So, hello to everyone, good morning. I'm Vasilis Rokai. By now, probably you sort of know me. I will be chairing the pre-lunch session, and we have the pleasure today in the morning to kick off the session with a talk by Jerome Faist from ITAMP Zurich. So, Jerome, the stage is yours. So,
thank you, Marcel. Well, thank you all. Thank you for putting us together in this very nice program and getting us here. It's a great way of mixing communities. And so I will thank you for coming early. And sort of in the spirit of this workshop, I will show you a bit of a status of progress of our experimentally, really fundamental, those are really fundamental experiments, on sort of trying to understand how can you use, and to which extent can you use vacuum fluctuation to modify the quantum Hall effect. Two names that we'd really like to emphasize, Josephine Entler and Lorenzo Gradiotto, have really been the two students now who are working on this, and they're really doing a fantastic job. So, the background is clear. We know vacuum fluctuations are real. They are involved in spontaneous emission. They really are responsible for the lamp shift. What has been new is the fact that thanks to ultra-fast techniques, we actually have also ways to now detect, measure those vacuum fluctuations, mostly by not trying to measure the energy of the field, but measuring the field directly. So you can think of it as just applying the field operator to vacuum. And of course, we know the expectation of the field operator is non-zero. It's only, let's say, the expectation, the average, of course, is zero, but the expectation, if you now make a correlation experiment, and what I will be concerned today is more about using cavities, and by using cavities enhancing vacuum fluctuation or controlling vacuum fluctuation. This is, of course, what Purcell came up already so many years ago, but this great idea. And behind it is really this conceptual question, which is quite fascinating. It's part of the questions that we bring us all to that same workshop is, can you use cavities to modify the state of matter? And to which extent? And of course, the properties that you're thinking of are superconductivity, for electricity, for magnetism. And the big question is, can you control many-body phases? Can you control these low energy scales of this matter? And obviously, in a sense, we know that it's not easy, because we know that the photon is very light, the wavelength of light is very long compared to the wavelength of the electron, and therefore, if you just think in terms of energetics or density of state, most of the time you say, well, I can neglect this. So obviously, this is the reason you will actually try to put yourself in the corners of physics where you can artificially bring the wavelength of your light down by using metallic nanostructures, and you also select systems where you have competing orders or competing phases, and there maybe just a tiny amount of vacuum fluctuation can steer you in one direction or the other. So our approach has been to use electrons in a very nice, very clean two-dimensional electron gas, and coupled with a magnetic field. And those, of course, what we showed many years ago is that once you have those electrons in a 2D gas, they can couple very strongly to light. And they couple very strongly to light because the cyclotron transition is extremely strong. It has a very large selective strength. It's a very nice transition because you can tune it by changing magnetic field. And here is a plot, for example, of a structure where we had a cavity. It was done in a metallic cavity. And what we show here is that when you basically observe, you should observe in this electron system the fact that as you increase the magnetic field, you should see a linear dispersion of the electron. But since this electron is now coupled to a cavity, what you see is two polaritons So light matter hybrid and light matter coupled excitations. And what matters here is the fact that the splitting, the energy separation between the upper and the lower polariton is of the same order as the energy of the cavity. And that, of course, means that in that sense, you're in the ultra-strong coupling. Yeah.
It looks like there are actually 3 branches.
Right, okay. This is right, of course. And it comes about because no cavity has ever, and as was discussed yesterday, absolutely a single mode. So there is an excited mode that we don't see, and of course, we can describe those things in very well. But I say, for me, what I just wanted to really stress is when we do this is of course, a collective strong, ultra-strong light matter coupling, meaning what you excite here is really in the decay approach, you excite a collection of electrons, you're looking at the excitation of that collection of electrons, and that is the mode that has this very strong coupling to light. All the other modes are dark, and of course do not, if you want to react to light. So this is, you should never interpret that energy as being the energy per electron. It is not. This is not the energy, does not represent the coupling energy per electron. So obviously we worked quite a bit in looking at the optical properties of such systems, but what, for me was very interesting is thinking, okay, now if you describe, when you describe that system, what you can show is if you're in this regime, you need to take the anti-resonant terms of the Hamiltonian, and if you take the anti-resonant terms of the Hamiltonian, you can show also that you are basically modifying the ground state. And so to which extent now the fact that you need to modify the ground state affects other properties like transport. So what I really wanted to, the goal was to investigate the quantum Hall transport in the presence of this very strong light matter coupling. So, what we are dealing is, as I said, electrons doing cyclone orbit. If you put a magnetic field, you have Landau levels. Now, of course, the transport will be very much depending on whether your Fermi energy is within one band or between bands. And, of course, as I said, the nice thing is that when you change the magnetic field, the splitting between these Landau levels will be linearly increasing with the magnetic field. And now, if you do a transport experiment, we know what happens. If you basically have your chemical potential of Fermi energy within a band, you basically see a linear resistance and a non-quantized value of the transverse resistance. But when we are now choose a magnetic field for which the Fermi energy lies between two Landau levels, we see the famous quantized values for the transverse resistance and zero resistance for the longitudinal resistance. Now, that also electrons have spin, and this is going to be also an important aspect of the work I'm going to be presenting today, is the fact that when you apply a magnetic field, you also split the Landau level. If you are low enough in temperature and you have a clean enough system, they will now be split, the Landau level split in two according to the spin of your electrons inside. And therefore, you see also the so-called odd plateau, and odd plateau means that your chemical potential lies between two Zeeman splitted Landau levels. But in terms of the what you observe experimentally, it's the same thing. It's a quantized value for the transverse resistance and zero value for the longitudinal resistance. So how do we make those cavities? Well, we make those cavities, in a sense, in an extremely simple way, you might say, because they are simply, an electrical engineer would describe that as a slot antenna. It's basically a cutout of a very highly conductive metal that has a certain shape. And, you can think of this as an LC circuit where, here, for example, we have the current that will be flowing the two-dimensional electron gas going along this way. And now the resonance of that antenna occurs because those two edges of this metal, this gold conductive metal, behave as a capacitor, and the current that flows around this cutout here will be the inductor. And as a result, you get a resonant frequency around 130 gigahertz or so. Yeah?
sorry, the terahertz field that you showed, the direction is for a particular mode, or?
Yeah, this is a very good question. And that actually, again, is one of the difficulties of thinking about those systems. In principle, you have to take into account all the modes of those resonators, and they have really a lot of them. So when I'm talking about the mode, it's a fundamental mode. Now, you're absolutely right. This mode that has an electric field in this direction corresponds to the fundamental mode. You will have excited modes for the field in that direction, but you also have excited modes for the field in the opposite direction. Now, of course, the higher you go in frequency, in the sense, the less confined those modes are, and therefore you might say, well, because of R, they will play a bit of a lesser role, but it's a very good point. Everything I'm going to be talking about assumes there is only one mode. It's clear that higher order mode will play a role, and that is very difficult to take into account. So, sorry, one thing which is important is now if you analyze, and the reason, of course, that we look at those cavities, at least initially, the initial idea was that, well, as was mentioned already in that workshop, if you think about the vacuum fluctuation inside such a cavity, we can very simply think of the electric field, or let's say the fluctuation field that you have inside the cavity, as being simply this 1/2 h bar omega of energy that you have to half of the time get to be in the form of a electric field. And therefore, what you have in the end is that the electric field, let's say this RMS value of the fluctuating field, is proportional to 1/square root of the volume. And therefore, by making those very tiny cavities compared to their wavelength, you're actually enhancing the vacuum fluctuations. So, for example, here, that 5 volts per meter, that would be this RMS value, is something like 10 times larger than 20 times larger than what you would have without the cavity. Now, of course, we want to measure inside the cavity, so what we take is we take a whole bar with contacts, and we imprint the cavity on top, and as you see here, the electric field, the horizontal electric field, will be, if you want, along the transverse side of the two-dimensional electron gas. So in color code, here is the absolute value of the electric field, and you see that the field tends to crowd a bit on the edge, and that's natural. Think about it as an electrostatic problem. If I have a metal edge, I will have more field. And be careful that also, I just warn you, this is the field for the uncoupled cavity. In that computation, we assume there was no 2D electron gas below. This is not the coupled system. Okay. Yeah, sure.
Do you have an estimate of how, what is the width of this area? The blue
Yeah, it's about a micron.
About a micron.
And
It's sort of like pretty large areas.
Yeah, well, what we are doing the simulations now, but you can sort of convince yourself it's even narrower when you actually now look at the coupled system. Now, of course, what is interesting is that the transport inside this quantum hole should be topologically protected. And of course, if you have a very clean system, electrons are doing cyclotron orbits in the bulk of your material, and therefore they don't contribute to transport. Obviously, if you now have electrons that are at the edge of the material, they basically do skipping orbits, and those skipping orbits are the ones that are carrying the current. Now, there was this also thing, even a slight amount of disorder doesn't hurt this picture, as was shown by Buttigieg many years ago. If you think of an electron doing the skipping orbit, if it hits an impurity, it doesn't go around and continue. So effectively, if you don't have too much scattering, you don't get back scattering on the edges. Now, the question is, can the vacuum fluctuation modify this picture? Well, strictly speaking, clearly yes. And because in the end, the vacuum fluctuations, this field that we are adding now because of the vacuum fluctuation and the cavity, is a potential that is there at the scale of the sample. So it's not a local impurity, and therefore it's something that in principle would induce scattering. And the question was also, well, maybe can it affect the quantization? This h over e squared resistance of the conductivity constant. Now, I will first talk about the scattering, and there what we did is an experiment where we compared In the same, of course, we get a sample where we pass the current in the long hole bar, and in that long hole bar we have two regions, one which has a cavity and one which has no cavity. And this is basically cool down in one single cool down. It's measured very low temperatures, something like 20 millikelvin in our cryostat. And in dark lines are the transverse and longitudinal resistance that you observe in the part of the sample that do not have a cavity. And you see what you really expect to see in such sample. That means very nice quantization. You even see some fractions here, the 5/3 fraction. And all in all, you expect that you see really what you would expect to see. And now what is striking is that the region in which we had this cavity showed a very modified quantization in the sense that mostly, especially around the odd quantization point, the resistance is now, the longitudinal resistance is not zero anymore. The value of the transverse resistance is also not quantized. Even don't miss, I mean, those are really not truly quantized. The blue line looks flat, but it's not really well quantized. And that really happens in this whole magnetic field range. Now, one thing which is clear is that if when we look, however, at very low, at basically zero magnetic field, we see that the longitudinal resistance has not changed, so the mobility of the sample remains the same. And we see also, as we had seen in other experiments, the fact that the Shignikov-Haas oscillations have changed. Now, how do we can interpret this this effect? Well, basically, we saw it as a scattering that basically scatters, and I will come back later on what type of scattering, but we think of it as a scattering that allows basically scattering from one edge to the other of the edge states. So this is the Pütiger-Landauer picture of this the quantum Hall effect. And now what we assumed is that the vacuum fluctuations are inducing some scattering, and they can be described as effectively a kind of resistance. Now, this was a model that was originally used to describe the let's say, the region between plateaux by Macker and co-workers. And so we adapted here by simply saying the model that we have here is a model where we assume there is this kind of what we call this rho x mu, which is kind of the resistance that is a 2D resistance which is coming from the vacuum fluctuations. And that the amount of scattering just depends on the geometry of that section. So we have here some scattering from edge to edge here, from scattering from, let's say, across the contacts and across the injection. So once you do that, well, you can basically use that model to, for example, assume that you that you measure the longitudinal resistance at the quantized plateau, and then you can try to see whether you can recover the transverse resistance that would be associated with that value of this rho xx that you find. And that actually worked very well. So in a sense, we can describe our phenomenologically as if we have a kind of a resistivity coming from the vacuum fluctuation. And that resistivity now has a energy dependence. We can do this experiment now for many magnetic fields, and we can see how much that resistivity goes down in field. Yeah?
Can I ask, so in this language, the resistivity is independent of, is isotropic essentially. So there's no.
Yeah, it's
no
isotropic, but
it's just a disturbance.
It's a tunneling. It's a tunneling. You just describe it as a scatterer. This is the Pütiger-Landauer picture. So you assume you see it as a scatterer, and the amount of scattering will be proportional to the length divided by width of your section. Yes.
No, sorry. Is it
Yeah.
rho xx? How can that be isotropic?
Well, okay. Yeah, good point. This is, of course, if it's rho xx, you say, well, why is it isotropic? No, but that's exactly this. The constitutive equation that matters here is this one. So you basically assume that each one of these segments has a tunnel barrier which reflects the innermost edge channel to the other side, and the amount of the strength of that tunnel barrier, or let's say that reflection coefficient, is given by this formula. It's 1 over 1 plus this parameter that you call rho xx times g, and that is the effective geometrical length divided by width aspect ratio. And as I said, this is the so-called network approach of the quantum Hall effect that was taken by, was assumed by McEwen and Zaffer and others. Yes?
So the vacuum fluctuations exist without the cavity too?
Yeah.
So the quantization in this case is
Perfect.
perfect, right?
Yes.
Perfect.
So why?
Yeah, you said like that there maybe there was a 20
Yeah.
factor.
Yeah.
So is that like
Yeah.
proportional of the
Yeah,
rate?
a very good point. Absolutely. And that is, in a sense, the reason why you need to go beyond that simple, let's say, you make the exact good point that it cannot be simply that the vacuum fluctuation or have a linear, let's say, influence on that resistivity. And that's why I'm insisting on the fact that we have those field gradients at the edges. So the vacuum fluctuation field, let's say the field that I have, is not the one of a plane wave that has a very long k, because if you have a resonator, which in that case it's at 140 gigahertz, it's something like millimeter wave. Now, having field gradient that drops over 1 micron is like 10 to the 3 change in your k. And as we will see, the nature of this anti-resonant process that we postulate is such that it can be allowed either by electronic disorder or by having a large gradient in the electric field. So that is, Eugene?
We know that the usual quantum Hall systems have semicircle law for x and x, y, as they deviate go through the plateau. Does this law is it still a data?
You mean you can express the, I know exactly what you mean.
Sigma xx changes, like
Exactly,
goes
exactly.
up and deviations
Right.
from sigma xy.
And that you can basically work it out. But what you mean is the value of rho xx, rxx and rxy between plateau follows this. Yeah. So the model I'm using is exactly based on that approach, if you want.
But an experimental data still shows.
So when we do without, let's say, okay, when I take those samples and I measure the ones without cavity between plateau, yes, we find this. So it behaves like you would expect. Of course, one has to be careful that that law works well if you neglect the spin splitting, let's say, I think for integer lambda levels, but not for spin split. But anyway, it works. So you get you get the same type of behavior. But now, let's say, of course, what we have here is an inhomogeneous system in which we assume in that model that, let's say, the quantization is perfect in the leads, and it's just perturbed inside the cavity. And so that's why this model, in a sense, works at the center of the plateau. We apply it at the center of the plateau.
I guess my question is just about the data itself.
Yeah.
For the data, do you see?
Yeah. So we see it, but for the unperturbed sample.
Without the cavity.
Without
the cavity messes it up, yes.
To be absolutely honest with you, I didn't check between plateaus, but I have very strong evidence that it messes up. Yes.
Quick question. Do you think edge reconstruction can be an issue here?
Yes. Well, this is edge reconstruction is one of the topics we should talk about. Absolutely. So, but let me go a bit further. So, what I want to say is that the slide comes for some reason I misplaced the slides. But let's say the assumption is that there is a process which is anti-resonant and which has this form where G is now the coupling, the light matter coupling, and which I will sort of just show later. But the important aspect is that it really contains matrix element which contains the overlap between wave function, and that overlap the wave function grows like LV square, so magnetic link square, and that's a 1 over B. So effectively, you expect this type of exponential decay, so the effect decreases as you make the magnetic field larger. So let me just sweep that because I don't have the time. Right. This is basically the picture that comes from Cristiano Ciutti. So the assumption is that what he said is, let's consider an electron, which is on one side, and now we consider simply the process in which we excite the electrons to the next Landau level, and at the same time emit a photon, and we basically, of course, immediately after, to conserve energy, we reabsorb that photon, and the electron goes down. And that is, if you want, the schematic for that process. And effectively, in this way, what we have this counter-rotating process, and it's allowed, and it will lead to a transport of electron only to the extent that I have either taken into account some electronic disorder, or, which is what he wrote in the paper, but also if you have, as I said, what he called photonic disorder, meaning I have strong field gradients. Because basically those strong field gradients, effectively, they give a momentum to the electron. They sort of blur the momentum of the electron. So, now, this is the picture. As I said, you have those edge states, and basically you make them talk to each other in using that process. Now, as we see, and that is the process that lift this quantization. Now, the second question, before I come back to that with a new experiment, is whether we do have any radiative corrections to the transverse resistance. And the question is, well, can we modify this, this value of 25 kilo ohm because of the cavity? And there was a prediction by Basil and Angel that it could work, so we tried to check it. And basically, what we did to, because I see the time is flying, what we did is we put the cavity inside, well, we put the whole bar now inside the cavity, not just the electrode, but we put the whole thing inside the cavity. We actually put that cavity inside a whetstone bridge, such that we could compare one sample that has the cavity with 3 other samples that have no cavity. When you do it, it gives you a nice chip like that. Kudos to Josephine who processed that thing. And long story short, we could look at the quantization, which appears in this signal, and effectively, okay, we don't find a significant deviation of quantization from the value that we expect. Still, let's say we're sort of still working a bit on the interpretation to really figure out what is the real error bar in that measurement. Of course, when you look, we are able to check that value at the level of 10 to the minus 5 or so. You say, well, the real people, they do that at 10 to the minus 10 or 10 to the minus 11. The problem that we have here is that we need to operate at very low temperature to see those effects, and we therefore can only use extremely small currents. So obviously, it's much more difficult in small samples, low temperature and small current, to have the same level of accuracy as what you have with big samples. So this is one of the problems. So what I would like, what I would like to show is kind of what I would call the hovering resonator experiment. Because instead of doing this experiment where we compare a cavity with no cavity, what we basically decided is to make an experiment where we actually could bring the cavity close to the 2D gas and keep the 2D gas the same. So the idea is that we process a sample where we have a series of whole bars. Again, we have an injection current here that goes along this, and then we basically have all those whole bars. And then on the other side, we have on the side a what we call a tip. It's actually a series of resonators that are brought on, upside down, close to that whole bar. And this is, of course, it's all, moved using a piezoelectric drive. And we can, of course, decrease the coupling or increase the coupling by moving the cavity closer or further away. We can even try to align the cavity. And this is, of course, very nice because now we can compare, for example, what happens when you're sort of 0.5 micron away to 35 micron away. And now this is the data, just to show you the whole thing. So this is the measurement done from over the whole magnetic field range for different value of the separation from 0 to 200 steps. Now, of course, most of the action we will see happens at this very low magnetic field range. But you see definitely there is a signal. We see a change in the transverse resistance and of the longitudinal resistance as we move our tip. And now if we look first at that very low magnetic field, the nice thing is we indeed see also there that as we increase the coupling and we bring the cavity closer, that will decrease the amplitude of the Schindler of the Haas, which is the thing that we republished in 2019 already. It's always nice to see it confirmed. And then the next step is to look at the initial out plateau, where again here you see a very strong dependence of the minima as function of position. If you look, so red is the place where the cavity has the strongest effect, and red is where I have the cavity the closest, and dark blue is when I'm at the furthest away.
So the distance is 0, 0, 100, 200, is that?
Those are in unit of steps in attocube steps. The 200 corresponds to 35 micron. So
35 microns.
Yeah, the maximum is to 35 micron.
So lambda over 10 or something.
You see, that's a very good question because you're right. You're exactly still within the near field, but I think here what matters is more the geometrical aspect. The width of the whole bar is 40 micron. You're moving your whole bar, your resonator at one width of resonator away. So clearly you see a strong effect.
But there's an evanescent field at
Exactly.
some level that is coupled.
That's exactly. Yeah, absolutely.
Okay. 8
Yeah. So just to show you how it works for this fraction and this other fraction, as we, let's say, of course, increase. And what we could do here also is to place now the cavity at different location and do a thermal activation. So you could look at how those minima are activated with temperature, and in this way measure the size of your Zeeman gap. We do that for the odd plateau, and we can see now how the Zeeman gap changes. And the beautiful thing is that we see that, as expected, when you are far away and you have the least, actually that data far is actually 1 millimeter away, so there you should really not see the cavity at all. You recover the G factor that you expect to see in this 2D gas, which is about 6 to 8 or something like that. And when we bring the cavity closer, we actually decrease the G factor. And so that's actually one interpretation now of this data, is the fact that we modify the effective G factor for the activated transport. And that is here for 3 different cavities, just to show you that this actually is really pretty consistent. And so the interpretation is that the G factor is essentially, re-normalized by the exchange energy. That was already pointed by Yannick many years ago. And what we basically are changing is exchange energy. And effectively, the exchange energy you can see it as depending on the dielectric function, not only the static one, but also the dynamical one. And with a cavity, we're effectively changing the dynamical dielectric also. That would be one way of seeing it. You can also interpret it, according to Cristiano, as the contribution of those sort of non-resonant, anti-resonant terms to the exchange energy. And so one other thing that you can actually check is also how does that change? Let's say, how do you change how does this activation energy changes with the distance of the resonator from the surface? And kind of, there we're still missing the simulations, but it gives you a feeling for, how does that, what are the length scale that are relevant, in terms of the photon field? And again, here, the length scales, you see that we within the first few micron, we already see a strong change. And that, for me, really highlights the fact that we are very sensitive to fringing fields. And that I'm really convinced. Of course, what would be nice is, and we will do, is to compute what is the effective coupling of the 2D gas for any separation. That you can do by electromagnetic simulations. This you can do. So now I just want to leave still a bit of time for the questions, just to show you some very preliminary data on fractions. If you look here again, we see very nicely a few fractions. Okay, there's one here, for example, and this one clearly improves as we remove the cavity. So this one seems not like very much the cavity. However, those two ones here seem to, be a bit improved. And now, okay, to be honest, if you look, you don't see much. But if you look as function of temperature, here I plotted in these two curves is basically 150 millikelvin. And clearly, when you move away, the minimum of the quantization has a bit gotten worse. So what it means is then when we compute for that cavity the activation gap, we find that the activation gap is slightly higher for the is slightly improved. The Laughlin gap, if you want, is hardened by the presence of the cavity. Well, this effect is still, again, I really want to stress, those are preliminary data that I'm showing in the spirit of the workshop, but this has to be confirmed. But it's really quite exciting because it really would mean that now it's another indication that we're affecting electron-electron scattering in those samples. So with that, I hope I showed you that indeed we can influence the quantum Hall effect using vacuum fluctuations in cavities. The nice aspect of the quantum Hall is we start from a transport where we understand what should happen because it's quantized. So deviation from quantization are much easier, let's say, to measure as, if you were to take another type of transport, it's always hard to know what you're starting with. And we don't have so far evidence for the renormalization of the quantum Hall resistance, but we have now a new experiment where we bring the cavity close to the 2D gas, which allows us a more quantitative measurement of the different quantities. And I would say we have experimental evidence for the renormalization of the G factor through the cavity. With that, thank you for your attention.
So we have some time for questions. Yeah. Thank you, Jerome. So I was wondering, did you see any interesting features relating states, particle symmetric quantum states, like 1/3 and 2/3? Is there any feature that suggests the cavity might be breaking particle symmetry somehow?
Yeah, I need to repeat myself a bit better also in fractions. Well, I just show you this. This is a sample where we have lower density. This is not a hovering cavity experiment. But what is striking here is, for example, that we see, if you want, around u equals 1/2, the quasi-particle don't seem to be very much affected, although some fractions seem to be much more affected than others. So that is definitely something where we're still trying to understand.
A quick question. With this new moving cavity,
Yeah.
what you expected
Mobility is what, right?
the mobility, the moving,
Yeah, it's not changing.
not change,
No.
even like a very small.
Okay, it's a good point. I will check, but so far, I'm saying that also because in all the other experiments where we're modifying much more, we have the cavity really imprinted on the whole bar. That's the one thing that never changed. With the mobility didn't seem to change and zero field. So everything was happening as you put in the field. But good point. We should check.
The dual thing never changes, you're saying?
Yeah. As zero field. But it's something which you're right. Since we have now this, it's something to look at. Yeah.
Bit of a softball, naive technical question.
When you move the cavity, do you have to worry about image charges and capacity?
It's grounded. So
you
there
need
is.
to be careful about that? Or is that-
Yes, of course.
Yeah.
Sorry. Let's say, one thing I want to stress is those two ligas are, you know, in kind of experimentalist parlance, said to be ungateable. And the reason they are kind of ungateable is they have heavy doping on each side of the chlorine wire. And that means that, let's say, they are insensitive to, they will screen any DC field which is outside. And that's why we can really safely exclude pure gating effects. And we, of course, also ground the cavity that is.
So one is
Yeah, thanks.
Thank you very much for the interesting. So you said that there is a gradient in the field.
Yeah.
Does that break the dipole approximation?
Yes.
So you don't have a homogeneous.
I believe this, a lot of the effects that we see arise from beyond dipole.
Okay, I guess we had. Are there more questions?
Okay, maybe this is a naive question, but suppose I take the picture of Fowler's of quantum Hall effect in a torus, and I didn't have those edge modes.
Yeah.
So then, and I put this in a cavity. Like, how would I imagine the breaking of this quantization?
This is such a good question.
It's not like naive.
Good.
Because I don't understand what.
I need to think about it. How can you? It could very well be that. Look, really from the top of my mind now, I suspect that if you don't have the edges, you're not going to see an effect. And that may be the reason why, in the end, we don't see a change in the quantization value. But look, this is just.
Comment. Actually, in Bordinos, you don't have edge, but you have the drop of RSX, so you would probably see still the same effects.
You're right, but you see, I would claim, of course, that Corbino, I have a physical edge, which is the edge of the metal. It's of course, topologically, I see what you mean, but let's say in terms of practical thing, I would have the metal, and I would have the metal, and have a fringing field on these edges that might do something. No, that's, yeah, I don't know.
Okay. So I guess we have to move with the next talk.